Hey guys, how you doing? This is Mr. Lee. This is part two of our chapter 15 lecture. So in the first lecture that we had in class, basically we just went over the conditions of what you have to check for inference for regression. So we have the mnemonic LINER, LINER. Independent and random were the exact same conditions we've always had. Linear, you're just checking that the data is linear. So how do you do that? You're going to look at the residual plot and look for patterns in the residual plot. Make sure that you read the residual plot from left to right and that there is no clear pattern. Okay, look at the zero line. You want to see that about half the dots are above and about half the residuals are below. Okay, for normal and equal variance, these two conditions kind of go together, and you have to kind of understand a little bit of what the actual population regression line is. And so for that, we have this diagram right here that's also in your textbook. If you just understand this one diagram, that is really your entire conceptual understanding of what is happening with this chapter, of what's happening conceptually in this chapter. So conceptually, you have this true population regression line, this red line that's going this way, and there's infinitely many um, points on this line. And if we were just to take one particular point, if we looked at one particular x value, or if we hold an x value constant, call it x1, there's not going to be the dots. There's going to be many, many dots, many y's that are associated with this x value, right? So there's going to be an entire distribution of y's. And if you look at the overall distribution of y's that's associated with this one x value, the entire distribution of y's is going to be a normal curve whose standard deviation is sigma. Okay, and then obviously the mean of that distribution is going to be on the line. So this population regression line is also called the mean of all your y's, right? Because it's the mean, it's the mean, it's the mean of the y's, right? So the mean of all the y's is equal to alpha plus beta x. So that is the true population regression line. Okay. So the conditions, okay, the conditions for normally and equal variance really go back to that diagram. And if you look at the normal condition, okay, you're going to go ahead and I suggest you make a normal probability plot. Okay, and what you're going to plot is your y's against your residuals. Okay, for the normal probability plot, you want to make sure that that looks approximately linear and there's nothing majorly strange about it, right? For equal variance, you're also going to look at the residual plot, look at the x equals 0 line, or the residual equals 0 line, and make sure that what you're seeing is basically about half the dots above, about half the dots below, and reading the residual plot from left to right, you want to see pretty much equal scatter, okay, about equal scatter, roughly the same scatter, okay? Okay, so in today's, so we checked all these conditions. Here's an example of how to check conditions. We went through this in class. Okay. So this is where we kind of left off, estimating the parameters. Okay. So if this is the true population regression line, we know that, we're going to take a sample. We're not going to know what the true population regression line is, but we're going to take a sample from the population and we're going to get a regression line from that sample. And we're going to get a y hat equals a plus bx, where a is an unbiased estimator of alpha, b is going to be an unbiased estimator of beta. Okay, and then here's the interesting part. Okay, so the LSRL computed from the sample data so our sample LSRL, okay, it estimates the population regression line. So the residuals from our sample regression line, the residuals estimate how much y has varied about the population line. That is kind of like the definition of um, what residuals are, right? Are just error in the y direction, right? And so this also goes back to um, this diagram right here. Okay, so here's the true population regression line. We're going to have some sample regression line, and that sample regression line, the residuals. Okay, the residuals are going to be estimating, well, how far off are we? Let's say our sample regression line is like that. Okay, well, the residuals are going to estimate, well, how far off are we in the y direction from the true population regression line? And so that's this. The residuals estimate how much y varies about the true population line. So because sigma is the standard deviation of responses about the population regression line, we estimate sigma by the standard deviation of the residuals. So S is equal to the square root of the sum of the squared residuals over n minus 2. Okay, the sum of the squared residuals over n minus 2. And again, the residual is going to be y minus y hat. It's always y minus y hat in that order, okay? Not y hat minus y, but y minus y hat. And that's just review. We learned that way back in chapter 3, I think it was. So now let's go back to Mrs. Barrett's class and the helicopter experiment. So they used Minitab software, and here's the Minitab output. So the coefficient of the constant. Well, your constant is just your this value right here. That's your little a. Okay, so that is your y-intercept. The coefficient of the drop height, well, drop height is your x variable, and the coefficient of it is your little b or your slope. Okay, so here's your equation of your sample regression line. Predicted flight time is equal to, there's your intercept, so negative 0.03761, okay, plus there's your slope. Okay, so not a whole lot of slope. That's almost a zero slope. Okay, and also the coefficient is also very small as well. Okay, and actually this coefficient should really be zero, because if you think about it, well, what is that coefficient? What is that y-intercept? Well, at a drop height of zero, our model predicts a flight time of, well, you can't really have a negative flight time, so that's just close to zero, right? And again, remember how to interpret little b. Okay, little b tells us that as the drop height increases by 1 centimeter, okay, the predicted flight time increases by 0.05 seconds, or 0.005, excuse me. Okay, here's a little comment about the y-intercept. And again, y-intercept should be zero, because if you have a drop height of zero, well, there's going to be zero flight time. Okay, well, negative 0.037 isn't zero, but it's close to zero. Now here we go. Our estimate for the standard deviation sigma is S right here. That's our little s. Okay, that is our estimate for sigma. All right, so let's go back to Old Faithful, and let's look at the population regression line. Okay, and this was the actual population regression line. Again, in most cases, you're not going to have these population parameters, but in this case, we do. We're going to show you what those population parameters are to instruct you, to teach you like how we do inference, how we deal with the statistics. But here's the parameters. We have alpha 33.97, beta 10.36, and sigma is 6.159. So let's say we go ahead and take the sampling distribution. Okay, the sampling distribution, so all the SRSs of size n equals 20. And let's look at the sampling distribution of B, because again, inference for regression is really inference about beta, right? So we're using B. So we know that it's normally distributed. We know that the mu is going to be the true beta. Okay, it magically lines itself up. And what is that? What concept is that? That's called unbiased estimator, right? It's a UEB is a UE of beta. So therefore, the mean of its distribution in its sampling distribution ends up being the true parameter, which is beta. Okay. What is our spread? So here now is your formula for spread. This you want to go ahead and write in your notes. Okay. So our spread of this entire sampling distribution would be sigma over Sx times root n minus 1, okay? Now, in this case, we actually know sigma, okay, and this is just for instructional purposes only. But in the real world and in actual problems that you do, you're never going to know sigma. So what do we always use instead of sigma? We use S in its place, okay, which is the standard deviation of the residuals. Well, what the heck is the standard deviation of the residuals? Well, that is this right here. The standard deviation of the residuals, S, is square root of the sum of the squared residuals divided by n minus 1. Okay, so that's what S is. And then it's over Sx times root n minus 1. Okay, times. So that, here's your equation for standard error of the slope. That is what we're actually going to be using. Okay, standard error of the slope. So go ahead and write that in your notes, please. Okay, so just like in everything else that we learned for inference, okay, the spread of the sampling distribution of the statistic is 1.3, okay, which is going to be a lot, quite a bit smaller than obviously the sigma, okay. All right, let's move on. So here's the equations that you need to write down. So this you may not actually need to write down because that's kind of, we just know this, right? If we're standardizing and we know sigma and we're standardizing, whoops, sorry. And we know sigma, we're just going to use the z is equal to the statistic minus the parameter divided by the standard deviation of the statistic. Okay, has standard normal distribution. However, replacing the standard deviation, sigma b, because we don't know sigma b. Well, why don't we know sigma b? Because we don't know sigma, right? So we're going to use SE of b instead. So what distribution do we use now? Not the Z distribution, but the T, the student's T, right? Guinness beer, student's T. So B minus beta over standard error of little b, right? And this is a T distribution. Now you also have to remember this. The df is equal to n minus 2, n minus 2. So in our little example, we had 20, n was equal to 20. So n minus 2 would be 18, okay? 18, df is equal to 18. So this figure shows the result of standardizing the values in the sampling distribution of little b from the Old Faithful example. Remember that n was 20, okay? And so we use 18 degrees of freedom. All right, so remember that constructing a confidence interval is always going to take the form of a statistic, okay, which is your point estimate, your statistic. So in this case, it's going to be little b, okay, that's the statistic, plus or minus the critical value times the standard deviation of the statistic, okay? So it's going to be little b plus or minus t star, because we're not going to know the standard deviation. We're going to use standard error, so we're going to use t star here, okay, and then times the standard deviation of the statistic, which we're using the standard error of little b. Okay, so when conditions for regression, when the conditions for inference for regression are met, okay, here is your confidence interval, b plus or minus t star SE of b. In this formula, the standard error of the slope, SE of b, is equal to S over Sx times root n minus 1. Okay, recall that S is the standard deviation of the residuals. Okay. Also recall that we're using n minus 2 for our degrees of freedom. Okay, so here's our helicopter experiment once again. Okay, so there's your A, there's your little b. Okay, there's your little s. Okay. The nice thing about this is it actually gives you, because this is little b, it actually gives you the standard error of little b, standard error of your coefficient. Okay, so that's really nice. So conditions are met, so we can construct a t interval for the slope beta with df equal to n minus 2, which is 70 minus 2 or 68. Okay, and now if you use the table, okay, use the more conservative df is equal to 60. Remember, we always go down. We don't round up, we don't round off, we go down. Okay, and this gives us a t star of 2.0. So here's our interval. So here's little b, that's right here. That's your point estimate or your statistic, plus or minus 2. There's your t star. Okay, 2 with 70 or 60 degrees of freedom was what we used. 70 minus 2, 68, or 60, since we're using the table. In your calculator, you would actually just put in 68. Okay, and then right here is your standard error. Okay, so that came from the table. So we love Minitab output. It's basically just plugging in the numbers into the correct spots. Okay, then go ahead and do the math. There it is, right? There it is. So remember how to interpret this interval in context. We are 95% confident that the interval from 0.00532 to 0.00612 seconds per centimeter captures the slope of the true regression line relating flight time y and drop height x of these paper helicopters. Not these paper helicopters, sorry, of paper helicopters. All right. Does fidgeting keep you slim? So here was an example we had way back when on NEA or non-exercise activity. And we came up with a model for predicted fat gain based on their change in non-exercise activity. Okay. And so perhaps the idea was, hey, perhaps fidgeting and non-exercise activity explains why some people don't gain weight, okay, even when they overeat. And this was a weird experiment, maybe a little unethical because you basically overfed these young adults. But they measured fat gain and change in energy use from activity other than deliberate exercise for each subject. There's the data. Okay, so that's just your X's and your Y's. And then from that data, you could actually just do a stat calc number 8, and you could come up with these, but they did that for us with Minitab. So thank you, Minitab. We love you. Okay, there's your A, there's your little b, there's your little s, there's your SE of little b. Okay, construct and interpret a 90% confidence interval for the slope of the population regression line. So I encourage you to go ahead and pause the video and see if you can construct and interpret that 90% confidence interval. Okay, so since we're doing inference, we're constructing a confidence interval, we need to go ahead and check their conditions, and our conditions are linear, L-I-N-E-R. Okay, and to check these conditions, you really need these two, okay, and maybe a normal probability plot, okay. But really, if you're just checking these two, you should be okay. Okay, linear, the scatter plot shows a clear linear pattern. Also, the residual plot shows random scatter of points about the residual line 0. Okay, so we're checking both of these graphs. This is the actual sample data. It's clearly, a linear pattern. Okay, independent and random, I'm going to skip. Normal, the histogram of residuals is roughly symmetric. So they used a histogram. Again, here I would recommend a normal probability plot, but they used a histogram and it looks unimodal and somewhat symmetric. Okay, nothing crazy, like nothing way too obviously, off of normality. Equal variance, it's hard to tell because there's so few points whether the scatter points around the residual line is about the same at all x values, but it really is hard to tell. Like the only weird one would be maybe like here, this goes from here way up to there, but those don't have the same x value. So yeah, I mean nothing major, no major departures here. We're good. So here's the do. So that's the state and the plan, right? And then here's the do. So we're going to use a t-distribution with n minus 2 or 14 degrees of freedom to find the critical value. So for a 90% confidence level, the critical value t star is 1.761. Okay, and to find this on your calculator, all you're going to do is inverse t. Okay, you're going to use inverse t. Okay, so when you turn on your calculator, okay, you're going to go to second distribution or second vars for distribution, go to inverse t. The density under the curve is it's a 90% interval, but again, you have to include one of the tails, so 0.95. Then your df is going to be 14. Paste that sucker, and what did your calculator spit out? 1.7613101111. Okay. So our interval is just, what's the interval? It's statistic plus or minus the critical value times the standard error, right? So it's your statistic plus or minus your critical value times your standard error. Okay, so this number and this number are for Minitab, and then this t star is, you just got it from inverse t. Okay, so there is your there are your two values, your lower and your upper bound. Conclude, we are 90% confident that the interval from negative 0.004747 to negative 0.002136 kilograms captures the true slope of the population regression line relating NEA change to fat gain for healthy young adults. Okay, so what is this again? So you're capturing beta. Okay, in your interval, what you're doing is you're capturing beta, or you're estimating what is beta, what is the slope. Okay, not the values, but you're calculating the slope. Okay. All right, so how about a significance test? Okay, suppose the conditions for inference are met. To test the hypothesis, beta is equal to some hypothesized value, you're going to compute the test statistic, t is equal to b minus beta null over SE of beta. Find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by HA. Okay, use the t distribution with df is equal to n minus 2. Okay, so there's a greater than, there's a less than, there's a not equal to. Okay. So what are you going to use for H null? Your null hypothesis is always going to be the same. It's always going to be that there is no relationship, no linear relationship between the two variables. Okay, but you're going to use symbols. You're not going to write that in words. You're going to say that beta is equal to 0. There is no slope. There is no true population slope. Because if there is no true population beta, if there's no true population slope, that means there is no line. There is no linear relationship between x and y. Okay. So guys, that's all I have for this video. I will see you in the next video. Okay.